43A. We're going to introduce matrix multiplication, which is a really weird thing to do. I talked to you about a digital photograph and making changes to that digital photograph. So if you wanted to make, so every pixel is 4 numbers, the 3 primary colors, and black. If you wanted to make it more red, you could just add a number to all of the reds, and the red would become darker. You could subtract a number from all of the blues, and it would become less blue. You could add numbers to the black, and the whole picture would be darker. Okay? But what if you wanted to move things around? What if you wanted to rotate 90 degrees or do other edits? Then you need to be able to do matrix multiplication. And it's a really weird system. And I'll show you a couple ways to do it, and you pick whichever way you like best. We're going to work on problems 25 to 49 odd. So we're going to start by doing something simple. We're going to multiply a 2 by 2 matrix by a 2 by 2 matrix. So 4, 3, 1, 2, and I'm going to multiply that by 6, 0, negative 2, 8. Now, you might want to multiply straight across, but that's not how it works. Okay? Yes. You could, but we're not going to. We're actually going to do it the hard way. So, this is going to result in a 2 by 2 matrix, which makes sense. 2 by 2 multiplied by 2 by 2 is going to be a 2 by 2. But the weird thing is, the matrices don't have to be the same size. They do have to have something in common, but they don't have to be the same size. So the way to multiply matrices is this box right here, which is row 1, column 1. It is made up of row 1 in the first matrix and column 1 in the second matrix. The entire row and the entire column. So here's what you do. You multiply this row by that column, and then you add them together. So you do 4 times 6, which is 24, plus 3 times negative 2 is negative 6. So 24 minus 6 would be 18. Okay? So this box here is row 1, column 2. So I'm going to multiply row 1 by column 2. 4 times 0 is 0. 3 times 8 is 24. 0 plus 24 is 24. So this box is row 2, column 1. It's made up of multiplying everything in row 2 by everything in column 1. 1 times 6 is 6, minus 4. 6 minus 4 is 2. And then the last spot is going to be row 2, column 2. And I take row 2 and I multiply it by column 2. That's 0 plus 16 is 16. And that is the multiplication of those two matrices. Okay? So, what do two matrices have to have in common in order to be multiplied together? Which rows? Rows in which one? Columns in which one? It's not rows in the first, columns in the second. It's actually the number of columns in the second has to match the number of rows in the first. So, this is a 2 by 2, and I want to multiply it by a 2 by 2. It's really easy to figure out if this is going to work or not. These two numbers need to match. Okay? So, one way that I think is easier to do it is, let's say I had 1, 0, 3, 0, 6, 1. And I wanted to multiply it by, so this is a 2 by 3. I could multiply it by a 3 by 2, which would look like this. 1, 0, 2, 3, 0, negative 4. And here's how I like to set it up. Set up the first one, 1, 0, 6, 3, 0, 1. And then you put the other one right here. 1, 2, 0, 0, 3, 4. And that kind of makes a grid. How big is my resulting matrix going to be? 2 by 2. So if I multiply a 2 by 3 and a 3 by 2, these 3's need to match. And this will tell me how big the answer is. So if you put the first one, just leave it where it is, and then move the second one up, that will help you in the multiplication, and it will also tell you how big the answer needs to be. So this box is the product of all of the first row and all of the first column, the corresponding parts multiplied together, and then added up. So 1 times 1 is 1, plus 0 is 1. Okay, the next one, 1 times 0 is 0, 0 and 3 is 0, 6 and 4 is 24. It's really nice when they throw in zeros. Makes your life easier. So 3 times 1 is 3, plus 0 is 3. 1 and, 3 and 0 is 0, 0 and 3 is 0, 1 and 4 is 4. That is my answer. Does that make sense? Okay. So let's say I had that times, so that's a 3 by 4. I have to multiply that by a 4 by something. It could be a 4 by 1, it could be a 4 by 10. It doesn't matter. So 1, 0, 0, 1, 2, 1, 0, 1. So that's a 4 by 2. How big is my answer going to be? So if I draw these over, and I draw this over, I have a 3 by 2. And then you just multiply the corresponding parts and add them together. So 1, 0, 0, 6. 1 and 6 make 7. 2, 0, 0, 6. That's 8. 0, 0, 0, 3. 0, 2, 0, 3. That's 5. 1, 0, 0, 2. And then 2, 0, 0, 2, which is 4. So that's my answer matrix. Now, you can take a digital photograph and you can multiply it by a specific square matrix. And what it's going to do essentially is rotate that 90 degrees. Rotate every pixel 90 degrees, or rotate it all 180 degrees. Or you can even do matrices that will flip it upside down, or flip it left and right, or any other change that you want to do. So anytime you edit a picture digitally, the computer has been programmed just to hit it with a matrix that does what you want it to do. Eliminate all the blues. Make it all red. Yes. Good. I was going to get to that. So this is A times B. Is that the same as B times A? No. In this case, if A is 3 by 4 and B is 4 by 2, if I switch them, 4 by 2 times a 3 by 4, that doesn't even exist. So matrix multiplication is not commutative. Okay, and we will deal a little bit more with matrix multiplication. So we'll get a little bit more in depth. If you take a look at your assignment, 25 just tells you to multiply C and D together. And then 27 is just a multiplication. 29's multiplication, 31, 33. What order do you want to do 33 in? So we certainly can't switch B and D, even if they're both square. If B is square and D is square and you multiply them together, you'll get one answer. If you switch them and you multiply them together, you're going to get a different answer. So here we could take -4 and multiply it into B, and then times it by D, or we could do B and D together and then bring in the -4. Which do you prefer? I would do B and D first and then move the -4 in, which means that matrix multiplication is associative. It doesn't commute. You can't move things around, but you can do the second half first and then bring in the first half. It is associative. Okay. 35. There are a couple ways to do 35. We could do A plus E first and then multiply by B, or matrices do distribute. So I could do BA and BE and then add them together. But which one's going to be easier? Adding them first and then multiplying will be easier. But they do distribute. So they are associative, they do distribute, but they do not commute. All right, 37. All right, 37, 39. 39 says G squared. You have to multiply G by G. Can you just go through and square everything inside G? No, that doesn't work. You actually have to do G times itself. Now, in order for G times itself to work, G has to be, it's got to be square. If G is not square, then G squared does not exist. If G is a 3 by 2, you cannot multiply 3 by 2 and 3 by 2 because the middle two numbers don't line up. So in order to square, G has to be square. 40, 41, you can do 43. Some of these might not be possible. If they're not possible, just write not possible. Okay, then moving on to number 45. Okay. How does your calculator figure out row echelon form? Well, the way we did it was we went through and we switched rows, we added rows together, we divided things, we subtracted, we replaced. Well, there's got to be an easier way. So your calculator actually does algebra. So let's say I had this matrix, and you're going to want to watch this. Let's say I had the matrix 1, 3, 4, 2, 6, 8. Oh, let me hold on. It's been a while since I've done this. Let me make sure I'm not. Oh, never mind. We're not doing that. Okay. So when we do reduced row echelon form, we end up with something that looks like this. And then answers. Right? Or if it's a 3 by 4, we end up with this. And then answers. And if it's a 4 by 5, it's the same pattern. It just has an extra row and an extra column. Okay? This pattern right here is called the identity. What does identity mean? It's the number you use that does nothing. So for addition, what is our identity? 0. 0 is the thing that does nothing. The other interesting thing about identities is if you take any element and you combine it with any inverse element, you get the identity. So 4 plus 0 is 4. That's what the identity does. If we take 4 and combine it with its additive opposite, which is -4, I get 0. Okay? And the third thing that identity has is the identity is always its own inverse. If you invert 0 using addition, you get 0. Because 0 plus what is 0? The only answer is 0. So the identity does 3 things. It does nothing, it's its own inverse, and it's what you get when you combine anything with its inverse. So if we move on to multiplication, what is the multiplicative identity? 1. 1 times anything is itself. Okay, if I combine 4 with its multiplicative inverse, which is 1/4, 4 times 1/4 is 1. And if I take 1 and I invert it, I get 1. So matrix additive identity is really boring. What matrix could I add to a given matrix and not change it? All zeros. So we never deal with the additive inverse of matrices. But this is the multiplicative identity. And it depends on the size of your matrix. So this is called the I2 identity, because it's a 2 by 2. This is the I3 identity, and there's an I4 and an I5. So we can move on to I5, I6, I7. And this matrix is the one that doesn't do anything. And it's kind of neat how it happens. So let's take and let's multiply this by the identity. So this is a 3, oh, well, whatever. A 3 by 3. So which identity do I have to pick? The 3 by 3. So 1, 0, 0, 0, 1, 0, 0, 0, 1. So my answer has to have 3 columns. Whoa. That's not good. And 3 rows. Now, what happens when I multiply those? Well, this gets multiplied by 1, and everything else gets turned into zeros. So that would be a 4. Now I move on to that second spot. This gets multiplied by that second column, the 1 in the second column, and everything else is going to be zeros. So this would be a 2, and then this gets multiplied by that, and everything else gets multiplied by 0, so that's a 6. So the identity is a way to go through and just pick out the ones that are already in that spot and eliminate everything else. And we end up with exactly what we started with. Now, if you take the identity and you make little changes, like if you move the ones in the corners up, then that's going to have the effect of taking all the information and not deleting anything, but it will rotate it. So you'll still have the same numbers, they'll just be in a different order. And that's how you do rotations and reflections. And you start to introduce negatives, and you can do different things. And it's really easy to make changes with a matrix. The other crazy thing is, you can multiply any matrix by the identity. So let's say I had this, and I multiplied it by the identity. So this is a 4 by 2. What identity am I going to multiply it by? It has to be the 2 by 2. So 1, 0, 0, 1. And if I draw the lattice, is that going to work? So I actually wrote it the wrong way. Sorry, guys. This is a 2 by 4. We would have to multiply it by the 4 by 4, which that's not what I wanted to do. Scratch that. Here's what I wanted to do. I didn't want to do that much work. Okay, now I have a 4 by 2. I need to multiply it by I2, which is a 2 by 2. Now, I'm going to end up with 4, 2, 1, 0, 6, negative 2, 3, 4. Okay? So any matrix can be multiplied by the identity that matches up with how many columns it has. So if it's an 8 by 7, we would multiply it by I7, and it would do nothing. Well, we know that the identity has more than one purpose. It does nothing, which we've just shown, and it's its own inverse, which makes sense. The identity times itself is going to be itself. And the third thing it does, if you take any element and its inverse, and multiply them together, you get the identity. So what does a matrix inverse look like? Well, it's the multiplicative opposite, which is a little hard to wrap your head around, and it's a little bit tough to figure out what a matrix is, what an inverse matrix is. There are a couple ways to do it. We're going to do one in a little bit, not today. But one thing we do know, if you have matrix A and you multiply it by A inverse, you should get the identity. So on that last section in your assignment, you have two matrices, multiply them together, and see if you get I2 or I3 or I4. If you do get I2, what does that tell you? Then they are inverses. If I take A and multiply it by this one, and I get something that's similar to the identity, but not exact, then they're not inverses. If you take 4 and 1/5 and multiply them together, are you going to get the identity? No, you get something close. You'll be close to the identity, which means you're close to the inverse, but not exact. So if you take a look at 45, you're going to take A and multiply it by B and see if you get I2. Does it matter what order you multiply them in? Does it have to be AB? No. Because A times its inverse is the same as the inverse times A. So it doesn't matter what order you multiply them by. And in order for a matrix to be invertible, what has to happen? What do we know about the size of a matrix if it is invertible? It has to be square. You cannot invert a non-square matrix. Okay? Now there's another problem. Some matrices are not invertible even though they are square. And those matrices correspond to infinite solution systems and no solution systems. Okay, if I had this matrix 1, 1, 2, 2, it is not invertible because it's the same equation. It's like saying x plus y and 2x plus 2y. Those are the same thing. So in order for a matrix to be invertible, it has to be a linear system that has one solution. None of the information can be the same. No two equations can be the same because then you can't invert it. Anyway, we'll talk more about that later. Hey, so your assignment is to go all the way to 49. Good luck.